Hello students, welcome to MEC 1321 Engineering Statics. My name is Dr. Stewart, and today we're going to go over a couple of example problems from sections 2.4 through 2.6 in the book. In class we did go over one example, but we didn't have enough time to go over the rest of the material, and so I just want to go over a few examples to get you guys comfortable with solving these types of problems. So let's check out example 2.6, which is an example from the book. In this example, we're given a hook that has two forces applied to it, and we're asked to find the magnitude and the direction of the resultant force. So the first thing we do is we list our knowns and our unknowns. So for the force vector 1, it has a magnitude of 600 newtons, and it is directed 30 degrees on the x-axis. And force vector 2 has a magnitude of 400 newtons, and it's directed 45 degrees on the y-axis. Now that we've listed our knowns, we can go ahead and list our unknowns as well. And let's list those. Where our unknown is the magnitude of the force vector Fr, and our other unknown is the angle or the direction of Fr. Now that we've done that, we need to craft our free body diagram. We should establish a coordinate system and define what is a positive and what are the positive directions in that coordinate system. So we establish an x and y coordinate system because this is a 2D problem. And we say that towards the right is a positive I direction, and upwards is a positive j direction. Then we put in our knowns, which is the magnitude F1 and the angle information for it, and the magnitude F2 and the angle information. And then we can also draw our force resultant, our unknown, as well as the angle that is associated with it. In this case, I assume that the force resultant is in the second quadrant of the coordinate system, which is the positive x and the positive y quadrant, due to F1 having a larger magnitude and kind of a little bit of angular information about it. But I could be wrong, and we'll prove that by determining the x and the y components of Fr. So now that we've crafted our free body diagram, we've put in all the dimensional information, we put in our knowns and our unknowns, let's go ahead and attempt to solve the problem. First thing that we can do is we can attempt to use scalar notation. In the notes, we discuss how we can determine the resultant force component in the x direction by summing the forces in the x, and we can determine the resultant force y component by summing all of the forces in the y direction. So with scalar notation, that's what we're going to attempt to do. Now, it's important to remember that with scalar notation, that we should always try to draw an arrow which indicates what is a positive senses that we're going to assume. And then at the end, we can determine if the solution to our problem is in that positive sense or in a negative sense. So the first thing we do is start with the the force resultant in the x direction, which is equal to the sum of the forces in the x. We assume that our positive direction is towards the right, so we put a arrow. We put our arrow here. And we put a positive sign next to it, meaning that we're going in the right hand, or directly to the right direction. After we do that, we need to apply some of those scalar rules that we learned. We can apply the simplified law of sines, and when we do that, we can do that for force vector 1 as well as for force vector 2. When we do that, for force vector 1, we find we have this force vector 1. We have an angle of 30 degrees relative to the x-axis, and we want to find this opposite side here. We want to find this component, and by knowing that it is the component that is adjacent to F1, we'll find that the magnitude of F1 in the x direction is going to be equal to the magnitude F1 times cosine of 30 degrees. When we do the same thing for F2, and we see that it is the adjacent side that has an angle between these two components of 45 degrees, we'll find that well, it's not the adjacent component, it's the opposite component because we're trying to find the f2x. If it's the opposite component, so it's opposite from that angle of 45 degrees, then we know that f2x should be f2 times sine of 45 degrees. Now that we've done that, we know the magnitude f1 and f2, we've put in the angular information, we can simply do algebra or put this into our calculator and find that the force resultant in the x direction is equal to 235.8 newtons, and because this is a positive value, we can say that it's directed towards the right. Now let's do the same thing for the y components, where if we look at f1, we know that the y component is going to be the opposite component, and when we are finding the opposite component, we're going to find that the opposite component is equal to f1 times sine of 30 degrees. And then when we do the triangle here, we're looking at the adjacent component because it's on the y-axis. And when we're looking at the adjacent component, we want to find it. We'll find it to be f2 cosine of 45 degrees. And also, it is important to note that we're including the sense or the assumed sense for each of these components. So in the case of the sum of the forces in the y direction, if we were to observe what the component should be for f1 and f2, we see that both of those components should be in the positive y direction. So we have a positive sign in front of f1 sine 30 degrees and then a positive f2 cosine of 45 degrees. If we look back at the sum of the forces in the x direction, for f1, it's clear based on the vector that the f1x component should be positive, and it's clear from the f2 vector that the f2x component should be negative. So for f1, we have a positive f1 cosine of 30 degrees, and then for the f2, we have a negative f2 sine of 45 degrees. So it's important to remember, what is the sense of the components based on our free body diagram. So now that we've added these guys together, we'll find that the force resultant component in the y direction is equal to 582.8 newtons, where since it is a positive value and we've assumed upwards is positive, that we can put an upwards arrow to distinguish its direction. Now that we've found the components of the force resultant in the x and the y direction, we can use Pythagorean's theorem in order to find the total magnitude of the force resultant, where the force resultant is equal to the square root of force resultant of the components in the x direction squared plus the components in the y direction squared. When we put in our numbers and we solve, we find that the force resultant is equal to approximately 629 newtons. Now that we've done that, we can look and we see that our component in the x is a positive, our component in the y is a positive. So the assumption that we made that the force resultant is in the second quadrant of this coordinate system, meaning the positive x, positive y quadrant, is correct, because we know that the force in the x and the y are going to be positive. With that assumption, we now know that the angle theta r is going to be from the x-axis counterclockwise from the x-axis, right? So now let's go ahead and use a simple trig in order to find that angle theta r, where the angle theta r is equal to tan inverse the resultant y component over the resultant x component. When we put those values in, solve using our calculators, we find that the resultant's angle relative to the x-axis counterclockwise is 67.9 degrees. And then finally, we can take all of this information and represent the force resultant in Cartesian vector notation, where the force resultant is equal to the components in the x directions times I plus the components in the y components times j, which is simply as indicated. Now let's what I want you guys to do is do this group activity. It was going to be a group activity in class. However, we did not have enough time to go over it. So what I would like you guys to do is to attempt to do this problem at home. Put your name as well as your student number over the top and submit it to class during the next time that we meet. This is a simple problem from the book, but the book that I got it from may be different from yours. So do pause this video and copy down this information and then attempt to solve this problem. Okay? So with this problem, we have a hook, and it has three forces that have their own magnitudes and orientations within a coordinate system. And it asks us to determine the magnitude and the direction of the resultant force. The first thing that we're going to do, of course, is list our knowns and unknowns. And then the next thing we're going to do is try to craft a free body diagram. I will give you a hint with this problem. It is advantageous to either use a scalar or Cartesian notation to try to solve for this problem. Okay? So, definitely take your time and try to solve this problem and submit it to me. Submit it to me in class. So let's go ahead and do another example. This is example 2.8. I believe this is an example from a little bit later into the book. Well, not later into the book, but an example from either 2.6 or 2.5 or 2.6. I'm not sure. But let's go ahead and attempt to do this problem. In this problem, we have a structure which has a force coming out of it which has a magnitude of 200 newtons. It is in a 3D right-hand coordinate system, and we are given certain angular information of this force vector. We're given 45 degrees relative to the z axis and 60 degrees relative to the y. And our unknown is the angle alpha, which is the force vector relative to the x-axis. And this problem asks us to express the force vector in Cartesian vector notation. So what do we have? We have certain knowns and certain unknowns. We know the angle beta, the angle gamma. We know the magnitude of f, but we do not know the angle alpha, right? So now that we've identified our knowns and unknowns, let's simultaneously try to craft our free body diagram, where we have our right-hand coordinate system, we draw our known force vector, we draw the angular information that we're given, and then we put in our unknowns. Now for this problem, let me go ahead and put in some of the other unknowns that aren't listed here. Fx, Fy, and Fz of this force vector, those are unknowns that we need to find in order to create that Cartesian vector. And let me clean this problem up just a little bit here in terms of changing the color of these unknowns, so it's more clearly distinguished. So Fy, Fx, Fz, and our angle alpha, which goes from F to the x-axis. So now that we've drawn our free body diagram, we've established a coordinate system, put our knowns as well as our unknowns, let's go ahead and attempt to try to solve this problem. The first thing we might want to do is actually to find the angle alpha. Since we are given two of the angles of the force vector relative to the axes, we can simply use the cosine directions identity in order to find that missing angle, where the cosine direction identity is cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. If we take this equation and rearrange it trying to solve for alpha, we can do the relevant steps here. Well, we can do the relevant steps here to get to cosine alpha is equal to the square root of 1 minus cosine squared 60 degrees minus cosine squared 45 degrees. When we solve this in our calculators, we'll find that cosine alpha is equal to plus or minus 0.5. And when we take that and we rearrange it further to find alpha, and we solve, we'll find that alpha is either equal to 60 degrees or it's equal to 120 degrees. And now the question becomes, okay, which one of these angles is the appropriate angle? So what we can do is by inspection, if we were to inspect, if we were to actually put the value of 60 degrees for alpha or the value of 120 degrees for alpha, we can kind of visually inspect what type of result we would get. And by inspection, if we were to have an alpha which is 120 degrees, it doesn't make any sense. Because if the alpha is 120 degrees, so alpha goes from the x-axis to the force vector F, if it was 120 degrees, then we'd be given a negative Fx component. So the component in the x direction would be a negative value. And clearly, when we look at the solution, when we look at the diagram that was given, it is clear that the force vector should be within a positive, should have a positive x component. So from that inspection, we choose that alpha equals to 60 degrees because it's the only option that makes sense. Now that we've selected alpha as 60 degrees, now we should have enough information to form our Cartesian vector. Now remember in our notes that the Cartesian force vector can be described in various permutations. One of the permutations is that the force vector is equal to the force magnitude times cosine alpha I plus f cosine beta j plus f cosine gamma k, right? So let's look at this form that we have here, and it's clear that we have the alpha, beta, and gamma, and we also have the magnitude. So we can simply directly put in the values that we have and solve for the Cartesian vector. And when we do that, we find that the Cartesian vector is equal to 100i plus 100j plus 141.4 k newtons. And in order to verify the solution, to verify that we have the correct solution, we can simply check this solution by using Pythagorean's theorem. So the force magnitude is equal to the square root of fx squared plus fy squared plus fz squared, right? We know the force magnitude is 200 newtons. We've calculated fx, fy, and fz, and if both sides of the equation are equal, then that means that we verified our solution and we have the correct solution. However, because the way that Pythagorean theorem is structured, if we were to put if we were to incorrectly assume that fx was a negative direction instead of a positive direction, we would not notice the error. So it's important for us to be consistent in terms of what is a sense of orientation for the components of the Cartesian vector. Okay. Now let's do example 2.9. In this example, we have a hook, or we have a pin, and it has two forces, a force F1 and a force F2 coming out of it. And we're asked to find the magnitude and the coordinate direction angles of the force resultant acting on the ring. So we need to determine the force resultant and its direction angles relative to the x, y, and the z axes. So let's go ahead and establish our knowns. We know the Cartesian vector form of F1 and F2, which also carries the directional information for each of these. And we need to find the force resultant in the Cartesian form, the force resultant magnitude, and the coordinate direction angles, or the cosine angles, alpha, beta, and gamma, that are associated with that resultant vector. Now that we've listed our knowns and unknowns, let's craft our free body diagram. In our free body diagram, we establish our right-hand rule coordinate system. We put in the known force vectors F1 and F2, and then we also describe our unknown, which is the force resultant and the associated angles alpha, beta, and gamma. Now that we've done that, since we're given F1 and F2 in Cartesian form, it should be very simple for us to find the force resultant in Cartesian form, where the force resultant vector is equal to the F1 vector plus the F2 vector. Now remember, with these types of problems, we're going to collect like terms for the x, y, and z components, which are described as the I, j, and k's, right? So if we were to put the F1 in pounds plus the F2 in pounds, if we were to rearrange these and collect the like terms, then we would find that the force resultant in Cartesian form is equal to 50I minus 40J plus 180K pounds. And clearly 50 is our X component, negative 40 is the Y, 180 is the Z component. So we can find our magnitude of the force resultant using Pythagorean theorem as force resultant x squared plus FRY squared plus FRZ squared, all of that square root. When we do the math, we'll find that the force resultant magnitude is equal to 191 pounds. Now that we have the magnitude of the force resultant, and we've also found the magnitude of each component, so the force resultant x, y, and z, we can now attempt to find the angles. Now remember the use of the unit direction vector. The unit direction vector, there was a number of relationships. The unit direction vector for our force resultant can be equal to the fx over f of I plus fy over fj plus fz over fk. But also the unit direction vector is equal to cosine alpha of I plus cosine beta of j plus cosine gamma of k, right? And if we collect the like terms and make equivalent the like components from each part of this equation, we'll find that cosine alpha is equal to fx over f, cosine beta is equal to fy over f, and cosine gamma is equal to fz over f, right? Well, we've calculated our f, the magnitude of the force resultant, and we know the components in the x, y, and z directions, those subcomponents of the force resultant. So let's go ahead and perform the calculation, right? So let's do that. Let's do the ratio part, fx over f, which is 0.2617, fy over f, which is negative 0.2094j, and then fz over f, which is 0.9422, right? And then we replace the ratio with the cosine alpha. So now we have cosine alpha is equal to 0.2617, and we make those sides equivalent. And then by simply doing the cosine inverse of each of these, we'll be able to find the associated angles, where alpha is equal to 74.8 degrees, beta is equal to 102 degrees, and gamma is equal to 19.6 degrees. And so clearly, with this part of the problem, it's important to understand the various permutations of the unit direction vector. So the different ways that we can find that unit direction vector and what are the relationships, right? The magnitude ratios, so fx over f, fy over f, fz over f, or the cosine angles, cosine alpha, cosine beta, cosine gamma. If we know these relationships, if we're familiar with them by doing example problems and doing our homework and exercising, then it becomes very easy to solve these types of problems. So now we just have one more page, or one more problem here to do, which is example 210 from the book. Now, this example, we have a right-hand coordinate system, and we have a ring that has a force vector coming out of it that has a magnitude of 100 pounds. And we're given two angles of that force vector. One angle, which is 60 degrees relative to the xy plane, and another angle 45 degrees, which is relative to a projection of the force vector relative to the x-axis. And in this problem, we're asked to express this force vector in Cartesian vector notation. So our knowns for this problem is the magnitude, which is 100 pounds, and we also know that we're given some of the angles. And what we need to find are the components fx, fy, and fz, such that we can construct our Cartesian vector. Now that we've got our knowns and unknowns, let's go ahead and create our free body diagram. We establish our right-hand rule coordinate system. We draw our known force vector. We also put in the angles that were given, and then we just put a little more information in terms of, this will form a right triangle. This here will form a right triangle, and there's some projected line on the x and y plane relative to the force vector. So now that we have this, let's go ahead and try to apply trig, some basic trig, the law of sines. Simplify law of sines, law of cosines, in order to solve for some of the components of this vector. So the first thing we can do is try to solve for, or to find the component in the z direction. So very quickly, if we look at our force vector, and we've crafted this triangle, it's clear that we have a right-hand triangle of this body where we have the projected line on the xy axis, and we have a component here which should be the FZ component of the force vector. So when we look at this problem in such a way where we have our magnitude, we have this angle of 60 degrees, and the force Z is opposite to that angle, then clearly we know that force Z, again, where we see that force Z should be positive, right? We see that force Z should be equal to the magnitude of F times the sine of 60 degrees, where force Z becomes equal to 86.6 pounds, right? Now, what's another thing we can do? The adjacent part of the triangle here, where we have that yellow line, we could call that F prime, which is a projection of the force vector in the x and y plane. Now, in that case, the F prime, clearly we can indicate what direction that arrow should be for F prime. We'll find that F prime is equal to the magnitude F times cosine of 60 degrees, where F prime is equal to 50 pounds. So now that we've found F prime, we can further decompose F prime into x and y components, because the triangle formed by F prime will give you an the Fx component as well as the Fy component, right? And if we look at F prime, we look at F prime and we look at Fx, we see that Fx is the adjacent component. And so when we have a triangle and Fx, we have an adjacent component, we know that the magnitude of Fx should be F prime times cosine of 45 degrees, which will give us a value of 35.4 pounds. And then if we look at the same problem and we look and we see that Fy is the opposite component, then we'll find that Fy is equal to a negative value, because if we were to construct it, we would see that the arrow for Fy should be going in the negative y direction. So we'll have a negative F prime times sine of 45 degrees, such that we'll get a negative 35.4 pounds. And this is basically how we've deconstructed this vector into into x, y, and z components. So it's very important, clearly it's very important to be able to identify the right-hand triangle and use the appropriate trig in order to determine the magnitudes of the subcomponents of that triangle. Now notice that with this problem, we're not doing a traditional problem where you have your x and your y axes, and on the x-axis is always cosine, and then the y component is always sine. It does not work that way in this course. Often we'll be given triangles that are in different types of coordinate systems. So it's important for us to be mindful of what is the opposite, what is the adjacent term, what should be sine and what should be cosine. Because if you do not, then you will have the answer wrong. So now that we've done that, we found the x, the y, and the z component, we can finally arrive at the Cartesian vector, where the force the force vector in Cartesian form is fxi plus fyj plus fzk. We simply put those terms in, and we'll find that our force vector is equal to 35.4i minus 35.4j plus 86.6k. And of course, in order to verify this solution, we can very simply put in those components x, y, and z into Pythagorean's theorem, and we already are given the magnitude, and if both sides of the equation are equivalent, then we've verified our solution. However, it's important to note that we must correctly identify the directions of the x, y, and the z components. And that means looking very carefully at our free body diagram and understanding visually understanding or interpreting what direction the components should be based on the resultant vector. And then finally we can solve for the angles, for the directions of this problem. And simply solving for the angles, we can use the relationship that we developed in the previous problem, as well as the relationship that's found in the notes, which is cosine alpha is equal to the ratio fx over f, cosine beta is fy over f, and cosine gamma is fz over f. And simply doing the cosine inverse of that will give us alpha equal to 69.3 degrees, beta equal to 111 degrees, and gamma is equal to 30 degrees. So clearly, there are systematic approaches to solving these problems. However, there's a lot of flexibility in what way or what system or what approach that you use. There's various permutations in terms of finding the Cartesian vector. There's various permutations in terms of finding alpha, beta, and gamma, our cosine directions. So it's important that you become familiar with the equations and become comfortable solving problems using those equations. The way that you'll be assessed in this class is your understanding of the theory involving these statics type questions. So it's very important for you to understand the theory, understand how to correctly set up a problem, and move towards solving that problem. So definitely take your time when solving these. Try to clearly go step by step and try to create a systematic approach that works for you towards solving these problems. Okay? So thank you for taking a little bit of time out of your day. Hopefully we won't be creating too many more of these videos. Hopefully now that the class has kind of settled down a little bit, we've gone through the first week, we've got the clickers going, we should hopefully have more time in class to go over these problems and be able to interact with each other in terms of what you're confused at as I go through the examples. So thanks for your time. I'm Dr. Stewart. See you guys soon.